our kind of standard enzyme kinetics. And we look at normal kinetics, if we were looking at a plot of rate versus substrate concentration, we get a variety of slopes, but typically we get some nice kind of straight line slopes, which are easier to interpret. But enzyme kinetics goes all sorts of weird. Okay? And even if we had strange things of that's supposed to be a parabolic shape, we can fit a curve to that really easily. Enzyme kinetics don't fit curves very easily. Okay? And that's where we get that kind of weird curved line there. And the biggest issue with that is that our rate changes through the course of time. Okay? And it levels out. It's one thing if it gets faster and faster because we can get a nice predictive pattern off that. So we're getting a distinct change in the rate when we change our substrate concentration, and that messes with ways that we can model it. So that's where we end up with several people contributing to this, Michaelis and Menton, and then Lineweaver and Burke. So they take a look at our general enzyme substrate system, which is that red box. We've got the enzyme plus our substrate. It can go to form the enzyme substrate complex, which can then go on to form product. We also have to recognize the enzyme substrate complex can fall apart. And so what they're now trying to do is tie all of the stuff that we in theory learned in 152 and kind of wrap that all into one neat bundle to try and explain the rates for enzyme reactions, okay, and how they process and work through. They end up going through a variety of assumptions and simplifications, and we end up narrowing that down into the Lineweaver-Burke plot, okay, which is that equation of a line. The big thing that comes out of that, we get two big constants that come out. Km, okay, which is roughly equivalent to the binding constant, or is sometimes referred to as a binding constant. So what this is referencing is the ability for the enzyme to hold on to the substrate. Okay, and we looked at a variety of ways to label that. Okay, and I kept, because it was defined from the rate constants, I don't remember exactly how that all paired out, but trying to nail it down based off the rate constants isn't the easiest. So what we can do is do a rough equivalence, which I believe I've got this equation right, to our enzyme times our substrate over the enzyme substrate complex. So this is why we can call it the binding constant, okay? Because we're looking at products over reactants, okay, where we're looking at the dissociation. So the smaller that value, the tighter our enzyme will hold. Okay? Why does that make sense? Well, if it's products over reactants, if it's a small value, that means the products are free enzyme and free substrate are very small values. Okay? Which would mean it's holding on to those, it's keeping them together and condensed as the enzyme substrate complex. Kind of makes sense? Okay. So that affinity is something that we can then use to describe our enzyme, which is kind of a neat thing to do. The other thing we can introduce is Vmax, okay, which is our maximum rate. Okay, which isn't a bad thing to go through and know for any particular enzyme. Okay, this is where we end up converting it across into the turnover number, which relates back to how much enzyme was present. Okay, so that's our Vmax. Correct me if I'm wrong, but I think this is right. Vmax over the concentration of your enzyme, I think, is the turnover number. It's something like that. Okay? That gets you an idea of how fast the enzyme can work. Okay? So both of those are useful constants or useful ways to describe our enzyme that we can then report out and have some like tables or collections of. Okay? We can also look at how potential other substrates, like maybe we're making a drug to inhibit the reaction. We can tweak how it affects the reaction by looking at what happens to the Vmax and what happens to Km. Okay, kind of makes sense? All of that conversion takes us into the equation of the straight line, which is the other big thing that we get out of this, because what we'll end up doing is interpreting graphs. It can be relatively difficult to interpret, okay, the curve, so instead we convert it out into a straight line plot, because that allows us to determine Vmax and Km relatively quickly and easily off of a straight line plot. Okay, and the straight line plot is just easier to interpret. So our big points off of that we have the slope is Km over V max, okay, which in and of itself isn't super useful because then we have two constants and we don't know what those are until we bring in the y-intercept. The y-intercept is 1 over V max. So then you can solve for V max if you have the equation of the straight line. If you know V max, you can then go through and solve for the slope, or substitute that into the slope and solve for your Km. Okay, so we can get some information relatively quickly off of a straight line plot. If we extrapolate that data out, we can then also determine the x-intercept. Okay, that has to be an extrapolation because we're going into the negative range and we can't have negative concentrations. Okay, so that has to be an extrapolation backwards. Okay, kind of makes sense? So those are the big things that we need to remember and use relatively quickly when we're looking at enzyme kinetics. So when we went through the derivation is trying to set up the context of how this is happening and what somebody else went through and did. You're not responsible for that derivation, you're responsible for the interpretations. Okay? Make sense? Okay. And I did forget to do a solve here, but we'll probably do it later today, so we won't stress about it right now. Okay. If we were to look at this curve, our original data, can we pull any information off of that quickly and easily? There are two pieces of data, right, that we want for every enzyme. What are those two pieces of data? Km and Vmax. So when you look at that curve, can you determine either of those? Vmax. Vmax is the maximum rate. What is happening to our rate on that curve? It's flattening out at Vmax. Okay? So we could go through and determine our maximum rate by saying roughly somewhere up there. Remember, it's, what is it, an asymptote? It never actually achieves that value. It just gets closer and closer and closer to it. I think that's an asymptote. So if we were to draw on our line to determine our Vmax, we're going somewhere slightly above it, okay, but not that far above it. And whatever that value would be, that's our now Vmax as an interpretation off of this. Okay, could we get the Km? If we look at our straight line, what did we need to solve for the Km? Okay, we could go to the x-intercept. That involves extrapolation backwards. I don't like extrapolation backwards. You're right, but ignore that. Just make sure you can't do that. We need the slope. Okay, but that's not it. What else did we need to solve for Km? You needed Vmax. Km is related to Vmax and the slope. Okay, so to solve for Km, what did we need to get first? Vmax. What do we have? Interesting. By looking at our standard plot, we do have the Vmax already. Can we use that to determine Km? Yes. How? Okay, so let's fix that. You don't have a slope. We're now referencing solely our standard substrate curve. This is the only curve we've got. And you can't say take the slope off of that because what happens to the slope? It changes, so that doesn't work out for us. What's that? What do you mean? Substitute in, oh, you're saying into the equation down here? That's the little squiggly lines there. So let's say we know the substrate concentration. Sure, do we know the enzyme concentration? That's not enzyme total, that's enzyme that's not involved in the enzyme substrate complex. So we won't know the enzyme, and we also don't know the enzyme substrate complex. So attempting to solve from that doesn't quite work for us. What do you mean the other equation?